The illusion of time suggests that what we perceive as time might not exist independently of our minds. Some scientists argue that time is a mental construct created to make sense of the continuous flow of experiences. This concept challenges the classical notion of time as a linear progression of past, present, and future. Human perception of time is influenced by our biological and psychological makeup, causing us to see time as a sequence of events. Our brains process sensory information to create the illusion of continuity and order. For example, when watching a movie, our mind stitches together frames to perceive a smooth narrative. Brain processing plays a crucial role in how we experience time, with the prefrontal cortex and other neural mechanisms involved in tracking and organizing events. Consciousness allows us to be aware of these processes, giving us the sense of a present moment. Neurons firing at different rates can lead to variations in how we perceive duration and sequence. Memory and anticipation are fundamental in shaping our perception of time, acting like mental bookmarks that help us navigate our past and future. Memories allow us to recall past experiences, while anticipation helps us plan and predict future events. The feeling of time moving faster with age can be attributed to the compression of memories over time. Cultural differences have a profound effect on how time is understood and valued across societies. Some cultures view time as cyclical, with a focus on repeating patterns, while others see it as linear, emphasizing progress and forward movement. Examples include the Mayan calendar, which is based on cycles, contrasting with the Western emphasis on linear timelines. Newton's concept of absolute time portrays it as a uniformly flowing entity, existing independently of external events. In this view, time progresses at a constant rate, unaffected by the physical universe or human perception. This notion was a cornerstone of classical physics, influencing scientific thought for centuries. In classical mechanics, time serves as a fixed backdrop against which all physical events occur, providing a stable framework for predicting motion. Calculations in this realm assume time to be both absolute and constant, simplifying the analysis of mechanical systems. This approach allows for the application of Newton's laws to predict future states of systems with precision. The intuitive appeal of the classical time model lies in its alignment with our daily experiences of time as linear and unchanging. We perceive events happening in a sequential order, reinforcing the idea of time as a steady progression. This model resonates with our innate sense of a past, present, and future, making it conceptually accessible. Modern physics exposes limitations in classical physics time concepts, particularly through Einstein's work on relativity. Classical physics cannot account for time dilation effects observed at high velocities or strong gravitational fields. These discoveries highlight the need for a more dynamic understanding of time in explaining the universe. Einstein's special theory of relativity revolutionized the concept of time, introducing the idea of time dilation. According to this theory, time is not absolute but can vary depending on velocity and gravity, leading to differences in the passage of time for observers in different frames of reference. A famous example is the twin paradox, where one twin ages faster than the other when traveling at near-light speeds. Gravity's influence on time is a cornerstone of Einstein's general theory of relativity, where time is affected by the curvature of spacetime around massive objects. Near a massive body like the Earth, time runs slower compared to regions farther away in space. This effect, known as gravitational time dilation, has been confirmed by experiments such as atomic clock measurements at different altitudes. GPS satellites provide a practical example of time dilation, as their clocks tick faster than those on Earth due to weaker gravitational fields at higher altitudes. To ensure accuracy, these satellites must account for both gravitational and velocity-based time dilation effects predicted by relativity. By applying these corrections, GPS systems can maintain precise positioning data for navigation worldwide. The relativity of time raises profound philosophical questions about the nature of reality and existence. If time is not absolute but varies with observers' frames of reference, it challenges our understanding of a universal timeline. This has led philosophers and scientists to debate whether past, present, and future are equally real or merely subjective constructs. In quantum mechanics, time may be an emergent property arising from the fundamental interactions of particles. Some theories propose that time is not a basic element of the universe but emerges from the complex behavior of quantum systems. Experiments exploring quantum entanglement and superposition suggest that time could be a macroscopic phenomenon resulting from microscopic processes. Non-local correlations in quantum mechanics, such as entanglement, challenge classical notions of time and space. When particles become entangled, a change in the state of one particle instantaneously affects the other, regardless of distance, seemingly violating the notion of time-bound interactions. This phenomenon has been experimentally verified, questioning whether time is a fundamental aspect of quantum reality or an emergent concept. Quantum experiments like the double-slit experiment reveal phenomena that challenge traditional causality, as particles exhibit behaviors that seem to disregard temporal order. In quantum mechanics, the outcome is only determined upon measurement, creating scenarios where effect precedes cause. This challenges the classical view of a deterministic universe by suggesting that time may not be a fundamental constraint in quantum processes. In emergent theories, time is not a fundamental entity but a result of quantum interactions, akin to temperature arising from molecular motion. These theories propose that time emerges at a macroscopic level from the collective behavior of quantum states. An example is the holographic principle, which suggests that the universe's information might be encoded on a lower dimensional boundary, with time emerging from its dynamics. The block universe theory posits that all points in time are equally real, and time is merely a fourth dimension alongside space. In this view, the past, present, and future coexist, challenging our perception of a linear passage of time. This perspective implies that the flow of time is an illusion, as the universe is a static block where events are fixed and unalterable. Within the block universe theory, time is considered an illusion due to the static nature of spacetime, where all events are laid out in a four-dimensional structure. Our perception of time's flow is attributed to our subjective consciousness moving through this block, rather than time itself moving. This challenges the traditional view of a dynamic universe and suggests that our sense of time's passage is a cognitive artifact. The concept of classical causality assumes a linear sequence of cause and effect, contrasting sharply with the block universe's timeless perspective. In classical physics, events unfold in a chronological order, with past events influencing future outcomes. The block universe negates this sequence, proposing that all events are predetermined within the spatial-temporal continuum, rendering the classical idea of causality obsolete. In a timeless universe, the concept of free will becomes problematic, as all events are fixed within a block universe structure. If time does not flow, then the ability to choose differently at any moment is illusory, as all choices are predetermined. This challenges our understanding of agency, suggesting that what we perceive as decision-making is simply a traversal through a pre-existing timeline. The Einstein-Podolsky-Rosen paradox explores the phenomenon of quantum entanglement, where two particles remain connected, regardless of distance. This challenges the classical idea of locality, as changes in one particle's state instantaneously affect the other, seemingly without regard to time. Such non-local interactions suggest that temporal causality can be broken, leading to questions about the true nature of time in a quantum framework. Traveling at superluminal speeds implies moving faster than light, which violates causality by allowing effects to precede their causes. According to the theory of relativity, such speeds could lead to time paradoxes, where the sequence of events can be reversed. This presents a fundamental conflict with our understanding of a causally ordered universe, raising questions about the limits of speed and temporal sequences. Some theories, such as retrocausality and the many-worlds interpretation, propose mechanisms for maintaining consistent causality even within a framework that allows for temporal anomalies. Retrocausality suggests that effects can influence past events without logical contradictions, offering a potential resolution to paradoxes. Meanwhile, the many-worlds interpretation posits that all possible outcomes occur in separate, branching timelines, preserving causality in each. In the quantum world, defining a present is challenging, as particles do not have definite states until measured, leading to superposition. This lack of definiteness blurs the line between past, present, and future, questioning whether a unique present moment can exist. Quantum experiments show that the concept of an absolute present is not easily applicable, as entanglement and probabilistic outcomes disrupt a clear temporal demarcation. The thermodynamic arrow of time suggests that the directionality we perceive is due to the increasing entropy in isolated systems. Our experience of time moving forward aligns with the second law of thermodynamics, which states that entropy or disorder tends to increase. This principle implies that the past has lower entropy than the future, guiding our perception of time's one-way flow. The second law of thermodynamics establishes that in any energy exchange, if no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state, known as entropy. This law is crucial in understanding the arrow of time, as it dictates that systems evolve towards greater disorder. In everyday terms, this explains why spilled milk doesn't unspill and why time appears to move in a single direction. Entropy is a measure of disorder within a system, and its increase over time is linked to our perception of the past and future. As systems naturally evolve towards higher entropy, we remember the past, when entropy was lower, and anticipate the future, where it is higher. This principle is evident in natural phenomena such as ice melting, where structured states, low entropy, move to disordered states, high entropy. Several alternative explanations explore why time seems to have a unidirectional flow, beyond entropy considerations. One theory posits that psychological processes in the brain create a narrative, giving the illusion of forward movement in time. Another theory suggests cosmological expansion, where the universe's growth influences our perception of time's directionality. The concept of time reversal is explored in physics through scenarios like T-symmetry, where physical laws remain invariant if time is reversed. However, in practice, true time reversal is unlikely because it would require reversing all processes, including entropy increase, which is statistically improbable. The thought experiment of a reverse movie, where all actions are played backward, highlights the conceptual challenges of reversing time. Cultural time varies across societies, with some viewing it as a linear journey while others see it as repetitive cycles. For instance, Western cultures often emphasize punctuality and schedules, while many indigenous cultures perceive time as interwoven with natural cycles and communal activities. This diversity highlights how cultural norms shape our perception of time as a social construct. Different cultures measure and define time using unique systems, reflecting their historical and environmental influences. The Gregorian calendar is widely used in the West, focusing on a linear progression of days, months, and years. In contrast, the Chinese lunar calendar incorporates both lunar and solar cycles, illustrating a more cyclical understanding of time. Cyclical versus linear time concepts are deeply rooted in religion and philosophy, influencing how societies perceive existence and progress. In Hinduism, Time is seen as an endless cycle of creation and destruction, known as Kalachakra. Meanwhile, Western philosophies, influenced by Christianity, often depict time as a linear path leading to a final judgment. Economic and technological advancements reshape our understanding of time, emphasizing efficiency and productivity. The Industrial Revolution introduced the concept of the workday, dividing time into productive units for labor and profit. Today, digital technology and the gig economy further blur traditional boundaries, creating a 24/7 society where time is constantly managed. Language profoundly influences time perception, as linguistic structures shape how we conceptualize and communicate temporal concepts. Some languages, like Hopi, lack specific tenses, leading speakers to perceive time as holistic and event-based. In contrast, languages with multiple tenses, like English, encourage a linear perception of past, present, and future events. In timeless physics, there are approaches that seek to eliminate time as a fundamental quantity by focusing on the underlying laws of nature rather than time itself. Some theories propose that time should be viewed as an emergent property, arising from deeper physical phenomena. This challenges the traditional view of time as a primary dimension and suggests it may only be a useful abstraction for describing certain processes. The Wheeler-DeWitt equation is a key concept in quantum gravity that suggests a timeless universe where the wave function of the universe does not depend on time. This equation implies that the universe's evolution can be described without a temporal parameter, aligning with the idea that time may not be a fundamental feature of reality. This has profound implications, suggesting that our perception of time is a result of viewing a static equation from within the system. Derivative time theories propose that time can exist as a derivative of spatial or other variables, rather than as an independent entity. In such models, time emerges from the interactions and relationships of other fundamental quantities, offering a different perspective on the nature of reality. This approach can be seen in certain quantum gravity theories, where time is not a primary component but a secondary effect. The absence of a true time dimension leads to significant philosophical consequences, questioning the nature of change and existence. If time is not fundamental, then concepts like past, present, and future lose their intrinsic meaning, affecting our understanding of causality and identity. This perspective challenges the linear progression of events, suggesting that our experience of time is a product of cognitive frameworks rather than objective reality. The relationship between free will and determinism is intricately linked to our perception of time, as time influences how we make decisions and perceive choice. In a deterministic universe, where all events are predetermined, the flow of time might merely be an illusion of sequential choices. However, theories in quantum mechanics introduce elements of randomness, suggesting that time and decision-making might be more interconnected with consciousness than previously thought. In a deterministic universe, every event is predetermined, suggesting that free will might be an illusion. If past, present, and future are fixed, our sense of making choices could be a cognitive artifact. However, some argue that human consciousness and complex decision-making might introduce elements that challenge this deterministic view. Quantum mechanics introduces randomness and indeterminacy through phenomena like superposition and entanglement. Particles do not have definite states until measured, leading to probabilistic outcomes rather than predetermined ones. This inherent randomness could imply that the universe is not entirely deterministic, allowing for free will within certain constraints. The link between consciousness and time perception is crucial, as our brains create the sense of a temporal flow. Our awareness and processing of sensory inputs allow us to experience a present moment and anticipate the future. Studies show that neurological activity influences how time is perceived, indicating a deep connection between mind and time. Different philosophical traditions offer varied interpretations of time's relation to free will. In existentialism, time is a dimension of human freedom, allowing for authentic choices and responsibility. Meanwhile, determinism suggests that time's linear progression limits free will, as all events are causally linked and predetermined. The future of time research involves exploring new physical and philosophical approaches to understand time's nature. Advances in quantum physics and cognitive neuroscience may provide fresh insights into time perception and its illusion. Interdisciplinary collaborations aim to address key questions about time's fundamental role in reality, leveraging technological advancements for innovative experiments. Current experiments in quantum physics investigate the nature of time through quantum entanglement and superposition studies. Researchers are exploring time-dependent quantum systems to understand how time may emerge from quantum mechanics. Notable experiments include those examining the temporal correlations between entangled particles, which challenge classical time concepts. Key questions for future theories include whether time is a fundamental aspect of the universe or an emergent property. Another critical inquiry is how time relates to space and matter, particularly in extreme conditions like black holes. Understanding the arrow of time and its relation to entropy in a quantum context also remains a crucial focus. Interdisciplinary approaches between physics, neuroscience, and philosophy aim to bridge gaps in understanding time's nature. Collaborations are exploring how neural processes influence time perception and whether philosophical insights can inform quantum theories. These efforts seek to create a unified framework that accounts for both scientific and experiential aspects of time. Technological advancements such as artificial intelligence and virtual reality may significantly alter our perception of time. These technologies can manipulate temporal experiences, such as speeding up or slowing down perceived time during simulations. Researchers are examining how these tools might influence our understanding of subjective temporal flow and its implications for daily life.